Am I audible? If audible, please put us in the chat. Okay, fine. Thank you. Hello everyone, and warm welcome to day 7 of our data science and AI add-on certificate course with industry internship. And thank you all for joining today. As you know, I am Alphy Mathew, research engineer at IPSR Solutions Limited. Okay, before I start, I will share my screen. Is my screen visible to you? Just confirm in the chat. Okay, thank you. So today it's day 3 of our machine learning section, and welcome once again to this session. And in the previous sessions, we completed all the pre-processing steps and also we have prepared our data set for modeling. So today we will officially begin our journey to classification algorithms. And the first algorithm we are going to learn today is support vector machine, generally called SVM. Okay, so today we will understand how SVM works, why it performs well on many data sets, and how to train a SVM model on our loan approval data set. Okay, so by the end of today's session, you will not only understand the concept of SVM, also we will be doing it hands-on in our loan approval prediction case study. Okay, so before we begin or before we explain what is SVM today, let's take a quick revision of the 3 main types of machine learning tasks we have already discussed in the previous sessions. Okay, that is regression, classification, clustering. You guys all know right now, you guys all know what is regression, what is classification, and what is clustering. And also know that regression and classification comes under supervised learning and clustering comes under unsupervised learning. So before we go into classification algorithm, we are just having a quick rewind because it is the base of the machine learning. So knowing this is very important. So also this will help us to connect what we learned in the previous session with what we are going to learn today. Okay, so I think you can see the image in the PPT. So in the first image, here you can see different people with their heights written above them, like 170 centimeter, 168 centimeter, like 100 centimeter, 95 centimeter, etc. So when our goal is to predict a continuous number like height, weight, salary, temperature, etc., that is everything that is numeric and keeps changing, we call that a regression. So here we are asking the model, can you predict the height? Okay, in such scenarios, the problem will be a regression problem. Okay, coming to the second image. The second image, same domain, but the problem is different. But here, we are not predicting a number. We are predicting, or we are just classifying a person as grown or growing. Two classes, grown or growing, and we are just classifying or we are just predicting the class or the category, either grown or growing for the particular person. So classification is all about putting data into categories or labels. For example, our loan approved or not approved, spam email or not spam email, then what, diabetic or non-diabetic, like that. So that is what we call classification, and that is exactly the type of problem we are solving in our loan project. So coming to the third image, on the third image, we can see that individuals are grouped into cluster A and cluster B. So notice here there is no labels are given to us. Okay, we are just grouping the individuals by their similarity. Okay, this process is known as clustering, and the clustering comes under unsupervised learning. So the algorithm in clustering finds natural groups in the data itself. For example, grouping customers based on buying patterns, or grouping students based on their learning behavior, etc. So always remember, in summary, regression means predicting continuous numbers. Classification means assigning or predicting a predefined classes or category, and clustering means grouping based on similarity. Okay. Now, we understand what classification is. So let's look different algorithms that can perform this task. Okay. So in machine learning, there isn't just one method for classification. There are many algorithms, and each one solves problems in slight different way. Okay. Before we start, let anyone know any of the classification algorithm before. If yes, put yes. If no, put no. Anyone heard or familiar with any algorithm or any name? Please respond. Like, just need to identify the audience. If not heard, simply put no. Okay, okay, no, no. Okay, fine. So uh, there are many algorithms comes under classification problems, and the most popular classification problem or classification algorithms are KNN, that is K nearest neighbors. Then comes support vector machine, that one we are going to discuss today, SVM. Then there is decision trees, then random forest, name based classification, logistic regression, and many more. Okay, so all these algorithms comes under classification problem. When we discuss about regression, there are also many regression algorithms. When coming to clustering, there are also clustering algorithms available. So here in this webinar, we are focusing to keep it beginner friendly, and we will be focusing on three algorithms, that is K nearest neighbors, KNN, then support vector machine, SVM, and we will be also looking into decision tree. Okay, so today in this session, we will be discussing or implementing or having the hands-on on support vector machine algorithm. Okay, we will be applying this algorithm in our learn prediction case study. Okay. Then what is the support vector machine or SVM algorithm means? We will be first discussing the concept and theory, then we will go into our coding window. Okay, so SVM is very powerful classification algorithm, and the basic idea or SVM basically tries to find the best possible boundary that separates one class from another. So simply think of like this. Okay, Imagine we have so many apples and oranges lying on a table. We have apples and oranges lying on a table. So if I ask you to draw a line so that all apples stay on one side and all oranges stay on the other side, what we will do? Okay, the problem is there are so many apples and oranges in the table. We need to separate these apples and oranges, and we need to draw a line. Okay, draw a line or put a surface in between these apples and oranges so that all the apples will be in one area and other oranges will be in the another area. What we will do is like try to draw a line or you will try to keep a surface that clearly divides them without mixing. Right. So this is what SVM does. It finds the best separating line or a plane between different groups. So I repeat, the SVM algorithm finds the best separating line or a surface between the available groups. So whenever a new data comes, suppose whenever a new fruit comes, the model simply checks, the SVM model simply checks which side it needs to be for, and then it knows the correct label. Okay, just as we divided apples and oranges in the table, exactly like that, SVM algorithm will separate or find the boundaries between different classes in the data set. And according to the boundary, when a new data comes, according to or looking into the boundary, it will assign the class labels for the new data. Okay, so this is the basic intuition behind SVM. Very simple. It is just to draw a perfect boundary so the classes are clearly separated. Okay. So here, look at this picture. In this picture, it is very simply explained what SVM actually looks. You can see two groups, class A and class B. Pink color points to class A and a blue shade color points to class B. So our goal is to separate these two classes, okay, using a plane or a line. Okay, when coming to a two-dimensional space, we can draw a line. When coming to a three-dimensional space, it will be a surface or a plane. Okay, so here in this PPT, we are saying about what two-dimensional image. So we see it as a boundary, as a line here. Okay, so here the diagonal line, the hyperplane, is what the SVM finds to separate the both classes distinctly. Okay, so it separates class A from class B as clear as possible. All pink dots are on one side of the line, and all the blue points are on other side of the line. So basically, SVM tries to find the best possible line that divides the two classes with maximum separation. Okay, and once this line is drawn, the model can easily decide the class of a new point by checking which side it falls on. So the basic idea or the goal of our how SVM work is that the best separating boundary or the hyperplane, so the two classes are clearly separated. Okay, to draw the hyperplane or the boundary so that the two classes are clearly separated. It is a goal of SVM algorithm. Now, we need to understand different types of SVM. There are two types of SVM mainly we focus on. First one is linear SVM and second one is non-linear SVM. Okay, then what is linear SVM or what is a linear problem? We need to understand it first. Look at this image. Okay, the first image, and in this image it represents a linear problem. What it means? Here you can see two groups of points, some plus points and some circles. Okay, and you can notice that here these points can be separated by using a straight line. Okay, we can separate, we can distinguish this circles and plus signs very effectively by using a straight line. Okay, you can literally draw a line in between both these classes, which is clearly separated. Right. So whenever your data can be divided using a straight line, we call that data as linearly separable data. So when our data can be separated or divided by a straight line, we call such data as linearly separable data. Okay, and for linearly separable data, we use linear SVM. Okay, so linear SVM will work fine on which type of data? It will be work fine on linearly separable data because linear SVM will be drawing straight lines or straight planes as the boundaries. Okay, now coming to the next image, non-linear problem. When you see this image, you can see that our plus signs are clustered in the center and the circles are surrounding them. Okay, the plus signs are in the center and the circles are surrounding them. By drawing a straight line, we cannot separate it. Look, for any straight line cannot separate all this plus on the one side and all the circles on the other side. We cannot achieve that. Right. So here we need some curly shapes or boundary like that. Okay. So this type of data, the data where the data cannot be separated or cannot be classified by a straight line, such data is known as not linearly separable data. Okay, not linearly separable data because a straight line cannot divide the data into two parts or into different classes. Okay, such cases, in such cases, we use non-linear SVM. So linear SVM will work fine in linearly separable data and non-linear SVM will work great in the non-linearly separable data. Okay. So in simple words, linear SVM creates straight line and non-linear SVM creates curved boundary. Either it will be a circle or would be a shape or would be a U shape or different curved surface or curved boundaries will be created by non-linear SVM. And the SVM algorithm, both linear SVM and non-linear SVMs, very beautifully handles this boundary, finding boundaries and etc. And we will see it in detail in coming slides. Okay, so just to check, I am asking if two groups of people are in a group. In a room, there are two groups of people. Suppose they stand clearly on left side and right side. Okay, in a room, there are two groups of people. Suppose one group wearing blue shirt and the other group wearing red shirt, and they are clearly stands on the left sides and right sides. Okay, in such case, which SVM will be better, linear or non-linear? Just put it in the chat box. Okay, linear. Others, please respond. I will explain once again. Suppose there is a room. In room there are in the left side. The people standing in the left side are in the blue shirt. The people standing in the right side is in the red shirt. We need to they are exactly as in the left side and right side. So if we need to classify them, which SVM will be there better? Linear or non-linear? A straight line or a curved surface? Yes, correct. Linear. Good. Now, if they are standing in a circular position, in the middle, the blue shirts are there, and surrounding the blue shirt people, our red shirt people are there, then which type of SVM will be better to find the boundary? We are now in a circular position. Yes, fine. Non-linear. Okay, good. Now, so before going into the detail, we need to understand two technical terms which are very important in the concept of SVM. That is, first one is hyperplane, and second one is support vectors. We already discussed what is hyperplane. Hyperplane is the boundary that we find, the best boundary that we find in between the classes. Okay. And also the second important term we need to understand is the support vectors. So we are now trying to understand it more better. So a hyperplane is simply the best possible boundary that separates the classes. The best possible boundary that separates the classes is known as the hyperplane. There can be many possible boundaries. Right, in SVM there will be many. In between those two classes, we can draw many lines. We can draw like this, like this, like this. So many lines we can draw in many orientations. So in there may be many lines, but what will be the hyperplane? Our hyperplane is the best possible boundary will be our hyperplane. Okay, so our aim will be your aim is to find the one boundary that separates the class most effectively, and that boundary is called the hyperplane. Okay, so when we have a two-dimensional surface, the hyperplane will be a line. Okay, you can see this is a 2D image, it will be a line. When coming to the three-dimensional space, you can see that the line will be a plane. Okay, the separation boundary will be a plane. So in short, the dimensions of the hyperplane depend on the number of features present in the dataset, which means if there are two features means two columns in the dataset, then our hyperplane will be a straight line. If three or more features, then it will be plane or a surface. Okay. So if I ask if our dataset have two columns, say height and weight, what will be the shape of hyperplane? Either it will be a line or a plane. You have the attributes height and weight. What will be the boundary? It will be a plane or a line, straight line. Yes, correct, straight line. You have the 2D, two-dimensional, it will be a straight line, and in the real world problem, it will be about two dimensionals and it will be like a surface. We cannot visualize it, but in real world problems, we are not sticking onto any two attributes. We will be using many n number of attributes. So there, either it will be plane or a surface. Okay, good. Now, the second important term, what is a support vector? So, to understand this easily, imagine this situation. Okay, we are trying to understand what is the support vectors. Okay, imagine two groups of students are standing apart. Okay, two groups of students are standing apart. If I try to draw a rope boundary between them, I am trying to draw a rope boundary. I am trying to build a rope boundary between these two groups. Okay, who will decide where that rope goes or where that boundary goes? The students standing far from the rope or the students standing very close to the rope? What do you think? if I will repeat once again, imagine there are two groups of students. I need to put a rope between these two groups of students. Okay, so which students will decide the position of the rope? There were the students standing far from the rope or students standing very close to the rope. Type far if you feel it as far from the rope. If type close if you feel it as close from the rope. Which students will be responsible for the rope position? Those who are close or those who are far? So close. Okay, which the position of the students either in the close or from the far position will decide the position of the rope. Close or far. Okay, fine. I got one answer and it's correct. Close, because the students, the ones standing close will decide where the rope to be placed. Okay, they are the actual boundaries, and according to that, students only the placed. Okay, similarly, this we can call in this scenario we can call the student standing close to the boundary as the support vectors. Okay, similar students, suppose we have some group of points. One group is green and other group is red. One group is green and other group is red. So our goal or our SVM's goal is to draw a boundary line that separate this group. Okay, to draw a boundary line that separate this group, and we call that boundary line as the hyperplane, the best hyperplane. The interesting part is that not all the points will affect the position of this boundary. So not all the points will affect the position of the boundary. Only few points influence the position of the separating line. And these special points that are closest to the hyperplane are known as the support vectors. So in this figure, this is the hyperplane. This black one is the hyperplane, the diagonal one. And the points that are close to the diagonal ones in both groups are known as the support vectors. Okay, so we call the special points are the support vectors. So these points are the right next to our boundary, and if the points move, the boundary also will move. If the position of the support vector changes, the position of the boundary also changes. So SVM pays attention to only these closest points than those in the far away places. So the closest points in the classes are responsible for the position of the hyperplane, and we call that closest points as the support vectors, and these points support the hyperplane, so we call them as support vectors. It support the hyperplane and they decide where the hyperplane should be placed. So in summary, support vectors are the closest data points to the hyperplane and the most important points in SVM, and these are the points that actually define the decision boundary. So without support vectors, SVM cannot find the correct boundary. Okay. Now let's try to understand how the SVM works from linear SVM to how it will work in linear SVM and how it goes in non-linear SVM. Suppose we have a small data set, say two attributes age and income and a class label class. According to age and income, we need to predict a either green or blue class. It's very dummy data just for understanding. So our goal is simple. When a new person comes with age and value, income value, we want to predict whether they belong to the green class or the blue class. This is our problem, and we are trying to solve using the linear SVM. Okay, so as we have only two attributes, our data is in the two-dimensional space. Okay, only age and income. Okay, so our boundary will be what? A straight line. So here you can see that in between these two classes, many possible lines can be drawn, right? We can draw many possible lines, different lines that separate the two classes. Just because a line separates the point doesn't mean that it is the best one. Okay, in different lines can be drawn. So just drawing a line is not our aim. Some lines may pass through the closest to the green points. Some lines or some boundaries may pass closest to blue points. Some may be tilted and so on. So the question is, how do we choose the best separating line? Okay, we need to find we in the sense the support vector machine needs to find the best separating line, and this is what the power of support vector machine algorithm. For that, it is not just picking a separating line, it is picking a line that is having maximum margin. I am repeating, it is the SVM is not randomly picking a line, it is picking a line that gives the maximum margin. Then what is margin? Margin is simply the distance between the line or the boundary and the closest data point from each class. Okay, the distance between the closest data point. We call that closest data point as support vectors. So the distance between the closest data point and the line drawn is known as the margin. So SVM tries to draw a line such that that line stays as far as possible from the green class and as far as possible from the blue class. If the line must be in maximum with the maximum margin. So as far as possible from the one class. Suppose in our case from green class and as far as possible from the blue class. So the larger the margin, the better model can generalize on a new data. So in simple words, among all possible separating lines, SVM chooses the one that sits in the middle and maximizes the gap between two classes. The line that maximizes the gap between two classes, that gap is known as margin. So we can say that the line that maximizes the margin is the best hyperplane or the best the classification, and this is what happening in linear SVM. So before we conclude the linear SVM, we need to we are going to just revise the main three important technical terms that we need to remember in support vector machine, that is hyperplane, support vectors, and margin. So I repeat it once again. Hyperplane, it is in our example, it is two-dimensional example. The hyperplane is the straight line that separates the two classes. If three or more dimension, the plane will hyperplane will not be a straight line. It will be a plane or a surface. And the best idea is that hyperplane is the boundary that separates class A from class B. So in SVM, the line we are trying to find, and the peculiarity of the boundary is that boundary will be having the maximum margin. Then coming to support vectors, these are the data points that lie closest to the separating line, and these points are very important because they decide where the hyperplane will sit, and also if we move the points, the hyperplane will also move. Okay, and also remember that the points that away from the hyperplane do not affect the line. Okay, then comes margin. Margin is simply the distance between the hyperplane and the nearest support vectors. Okay, okay, fine. Give me 1 minute. Okay, so this is how our linear SVM working. Now we need to understand how it will work for non-linear SVM. In linear, we are going to draw a line as our data is linearly separable. So we are now planning for how SVM works in linear or the non-linear data. So here in this image, we can see that class A, our red class is at the center, and our green class is surrounded with the red around the red class. So here, how do we draw a boundary? When a data is non-linear, SVM does something very smart. That is, instead of forcing a straight line, it learns to create a curved boundary. Okay, it learns to create a curved boundary. So for nonlinear data, we do not use a straight line, but we use a non-linear decision boundary, and this non-linear decision boundary may be curves, maybe circles, or any other shapes. So let us look how this curly surfaces are made by the SVM. So here, whenever data cannot be separated using a straight line in two-dimensional, SVM uses a simple but a powerful idea. It adds one more dimension. If our data is in 2D, then what nonlinear SVM do is that it will add one more dimension and make the data in 3D. Okay, so in 2D, imagine we have red points in the center and the green points forming a circle around them. That is in this like this first image. No matter how many straight lines we draw, we cannot separate them. So instead of struggling in 2D, what SVM do is that SVM transforms this data into the next higher dimension, that is 3D. Okay, when this non-linearly separable data is transformed into a higher dimension, it became linearly separable. Okay, that is, for example, we take each point from x and y points from this two-dimensional space and create a new value z, and we mapped all these points into a 3D space. Okay, so here in this image, you can clearly see that some points get lifted upward and some may stay down because we have added a third dimension, z. The third dimension is added. So some points are in the space and some points are lifted downwards. Okay, so in this image, we do not need any curly surface or anything. Here you can see that a plane can or a plane can easily cut both classes, can have a boundary. Right. So the assumption is that when a nonlinear separable data is brought to a higher dimension, that nonlinear data will become linearly separable. So after drawing this plane in 3D, SVM brings this separation back to the original 2D space. So first, the nonlinear data is taken into what the 3D space, higher dimension. In that higher dimension, it became linearly separable. So we have drawn a plane and separated it using the boundary found using the plane. And the next step, what we do is that after drawing this plane in 3-dimensional, that is in the higher dimensional, SVM brings this separation back to the original 2-dimensional space. So when we project the plane back to 2D, suppose we are this after finding the boundary, and when we project this plane back to 2D, it becomes a curved boundary. So even though the boundary in 2D looks curved, it is actually a flat plane in higher dimension. The, this is how our non-linear SVM works. So SVM converts the data to higher dimension where separation is easy and finds a straight hyperplane there and then brings the separation back to 2D as a curve. This is how nonlinear SVM successfully separates even complicated patterns. Okay, so this trick of making lower dimensional data to higher dimensional and finding the boundary, that trick is known as kernel trick. The kernel trick helps SVM data in a higher dimension without actually converting it manually. So think of like giving SVM a new view of the same data. In original space, the data looks mixed and messy, but in higher dimensional space, the data becomes neatly separable. So SVM then draws a straight line or a flat plane in that higher dimension. So when we bring that line back to the original dimension, it looks like a curved boundary which now separately which now separates the classes. So the beauty is that SVM never physically creates the higher dimensional data. Using a mathematical function called kernel, it calculates everything as if the data is already lifted. So all these processes are done using many mathematical formulas. We are not going deep into it. In the advanced levels of machine learning, we will be focusing on all these formulas, how these are converted. All the mathematical problem are included in there. But now as a beginner level, our focus is to understand the concept and to get hands-on. So in summary, remember that the kernel trick is a method used in separate machine to convert, that is non-linearly separable data, to convert the non-linear separable data into higher dimensional feature so that it is linearly separated. So these techniques enable the SVM to identify a hyperplane that separates data with the maximum margin even when the data is not linearly separable in its original space. Okay, so let's have a quick MCQ here. When SVM uses the kernel trick, what happens in higher dimension? Okay, my question is, when SVM uses a kernel trick, what happens in higher dimension? Options are, suppose I will type here, option A as data becomes circular, then option B as data will be linearly separable, option C as no changes. So the question is, when SVM uses kernel trick, what happens to the data in the higher dimension? Option A, it becomes circular. Option B, it is linearly separable. And option C, no changes. When applying kernel trick, what happens to the data in the higher dimension? Yes, correct. B. Because the in higher dimension, the nonlinear data become linear. Okay, fine. Now, there are different types of kernel available in the SVM. Okay, different types of kernel are there, different mathematical. Actually, these kernels are different mathematical formulas. We are not going such deep, but understand that there are linear kernel. Linear kernel means linear SVM. Okay, it's simply same as linear SVM. Then second type of kernel is polynomial kernel. Third is RBF kernel. RBF means radial basis function or Gaussian kernel. We call it like that. And fourth one is sigmoid kernel. There are different types of kernel: linear kernel, polynomial kernel, RBF or radial basis function or Gaussian kernel, then sigmoid kernel. Okay. The peculiarity is that if you are using a linear kernel, then the SVM will be linear SVM, and the boundary we will be finding will be a straight line or a plane. Okay, like this image. Okay, then coming to polynomial kernel, what happens is that the boundary will be something like U-shaped, exactly like the degree, like the shape will be controlled, or the curve will be controlled by the degree of the polynomial. Okay, so either if you want a one, or if your data is having a boundary with any U-shaped like boundaries, then polynomial kernel will be better in such cases. RBF kernel gives some complex, flexible, or closed or irregular boundaries. Okay, this is example of RBF. The boundaries will be somewhat closed, complex, irregular, or circular boundaries. Then, if you use sigmoid kernels, the boundaries, the found boundaries will be like S-shaped boundaries. S-shaped boundaries. You will be having S-shaped boundaries. Okay, so different types of kernels are there. What we do is that we need to apply all these kernels or all these type of SVM into our data, and we need to find which work better in our data set. That is our aim. Okay, so we will be taking our data set. We will be first looking for linear kernel, then we will find accuracy, then we will put polynomial kernel, then we will find accuracy, then RBF, then sigmoid, and so on. And we will compare which is better. That is our approach. Okay, so we are going to check how this will work in our Python sklearn library. Until now, we understood SVM concept. So what it does, or why it draws a boundary, what happens in linear or non-linear cases, etc. So we already have our data set cleaned, encoded, scaled, and split into train set and test set. So our data is full ready to fit into a model. So here we are trying this SVM, from the SVM library into our long prediction dataset. Okay. So before we start, okay, this is our collab that we have discussed up to here in the last class, and now we are the model building and evaluation part, and our first algorithm is SVM. Okay, so here we need to remind one important thing, that is Lab is an online platform. It does not remember what we ran yesterday. Okay, it will be giving you new sessions for when you log in for first time or second time, etc. It's around 6 to 5 hours we can work continuously in a collab. On the 6th hour, after some times the collab will get refreshed. Okay, so what I want to remember is that when you come back on a new day, or when you come back after some time, or when you come back after closing your laptop and coming to this collab window, what you want to do is that you need to rerun all the previous cells before running the new one. Okay, so as the collab environment session always refreshes, please remember that if you are doing the coding part by part, day one thing, day two another thing, like that, remember to rerun all the other cells before doing the new code. And also remember to upload the dataset here, because this is a new session. In this new session, our dataset is not there. So first, as we did in the first session, means second class of the machine learning, you go upload your dataset. I'm not going to upload now. You just upload your dataset and rerun all the cells up to the study, and then come and do this model building part. Okay, you need to run all of the libraries, everything. The one thing you can do is that you can go to every zero and run one by one from top to bottom. Remember that from top to bottom. You have to run this, then again run this. Like that, you can run one by one. Or another method is that just you can go and here run time. You can go and choose run all, run before, like that. Any method you can choose to run the previous cells. Okay. Now our focus is to uh, apply SVM in the loan prediction data set. We have our data set clearly split into X train, X test, Y train, and Y test. Up to this we have done in the previous class. Okay. Now what we want to do is first we want to create the object of the support vector machine algorithm. Okay, so first we are going to try linear SVM in the our long prediction data set. So for that, we need to create the object of linear SVM. To create the object of linear SVM in sklearn, we call SVM as support vector classifier, SVC. Okay, support vector classifier. And in order to run this, we need to import it first. Okay, we need to import it first. Look, this is the import statement from sklearn dot import svc. So we bring the svc class from the so that we can build SVM models. Okay, just you already know that sklearn is the main library of machine learning. Inside that, this SVM module is there. Inside that SVM module, this is support that is created. We are just importing that to our collab environment. Okay, after importing that only, we need to create the object. Okay, we need to create the object, and inside that kernel equal to linear. This means we are creating the linear SVM. Okay, now I have named this as SVM underscore model. If you want, you can name it as SVM underscore linear underscore model. So SVM model is SVM underscore variable SVM underscore. What we want to do is we need to feed the X train and Y train. It is our input data, right? X train and Y train is our input data. We want to give that input our X train and Y train into this model, and we need to train the model. That fit method. So this code implies this is the X train, this is the Y train. That is, this is the training data, training data with X and Y. Use this and find the patterns, find the boundary. The asking is going to find the linear straight line boundary, do all the tests and build a model, and that model will be Alphy. Okay. After this, the SVM model will be a sub SVM model built and holded in this video. Okay. Now we need to predict it using X test. Okay. We have our X test here. We have our testing data kept back for testing for unseen data. We have set apart a testing data. 20% of data is there. Take X test only from that testing data and give it to the model and ask the model to predict. Okay, now the model that we built will take the X values, the input of the test data, and will predict its own output, and all the output will be in this SVM pred. SVM pred is the predicted values of the SVM model. Okay, I'll just give one a name. You can give SVM linear pred or anything. You can give the name. So this SVM linear pred, SVM pred have the data or the answers predicted by the model. Okay, now we need to evaluate it. So to evaluate it, we need the correct answers and the answer given by the model, right? For the X test, where will be the correct answers are found for each X test? For each X test, the correct answers are there in each Y test. right? So we need to find the accuracy score by giving the correct answer and the predicted answer. Okay, so white test is the correct values of the input given here, the test data given here. The correct answer is the white test, and the SVM pred is the answers that predicted by the model built by us. And we are asking Python, by using this correct answer and the predicted answer, please find the accuracy score. So in order to find this accuracy score, in order to work this accuracy score, also we need to import the library. Look here. So we discussed the evaluation metrics as accuracy score and the confusion metrics before. So for both confusion metrics printing and for the accuracy score printing, we need to import it from the SQLN library metrics module. So from SQLN.metrics, import accuracy score, confusion metrics, then only our accuracy score will be working. Okay, so when we give that accuracy score, we can see that a point value is there, 0.816666, something like. It means that for this data, the model built in SVM model, the linear model that we have built, is showing 81%, around 81% of accuracy. Out of 100, 81 are correct. Some has gone wrong. Okay, this is what how we are doing the training step, the testing step, and the evaluation step. There are also our methods to evaluate, as I have already precision F1 score, recall, etc. So many are there, but at beginner level, we have score and the confusion metrics. Okay, now if you need to find the confusion metrics, to print the confusion metrics, very simple. Import it first as in the top, then come here and give confusion underscore metrics and give the correct answer versus predicted answer. Here our correct answers is in the y test and the predicted is in the SVM pred. So we are asking to print the confusion metrics and it will print it. Look, our confusion metrics. And here, remember that the SVM, sorry, it's not SVM, in SQLN's confusion metrics, the order is like this: PN, TP, FP, FN. Like, for example, you need to decode this confusion matrix as this image given here. Okay, so in our confusion matrix, we can say we have got 14, 21, 1, 9, 84. Then what this mean? I'm going to explain that. So here, in our confusion matrix, we know that yesterday or in the day before we have encoded 0 as non cannot be approved, that no as 0 and yes as 1. Okay, in our label encoder we used that. Okay, so if when we read this confusion matrix, we can read like this. So the value 14 means that it is the negative value because the model correctly predicted that loan cannot be approved. Simply it means that in actually loan cannot be approved and the model predicted loan cannot be approved. So that are the true negatives. That how many are there? 14 observations are there like that. So 14 are in the data set says that loan cannot be predicted and our model also predicted as loan cannot be approved. That is true negative is the first one, 14. Then coming to 21 means that in our actual data, loan is not approved. But our model said that we can give loan. Okay, there are 21 false positives. Now coming to loan approved and non-approved in 10, not approved. That is in actually loan can be approved, but our model said that loan cannot be approved. That is a wrong one, false negative. And coming to 84 is where actually loan can be approved and our model said that loan can be approved. So it is 84. So we can say that the total number of correct predictions are 84 plus 14. Always the diagonal will be the correct one and the total number of errors is 21 plus 1. Okay, when you do the maths like this, 84 plus 14 divided by 84 plus 21 plus 14 plus 1, we will get this one, 81% like that. Okay, and what is the accuracy? Total corrected by total number of observation gives accuracy, right? So instead of doing is using this function, you can use confusion matrix itself to find what? The accuracy score. Okay, now very simple. Now going to the next one. What the process is like, just change the kernel. Now we are trying RBF kernel. That is the radial basis function kernel or the Gaussian kernel. Here kernel equal to give it as RBF. Very simple. Again, fit the model using the train data, X train and Y train. Again, predict the output of the model using X test. Then find the accuracy using correct answers and the predicted one. So here to identify which is RBF, which is linear, I have renamed it SVM RBF model. Before it was SVM model, now it is SVM RBF model. So same process, repeat it. We can see that RBF is also giving the same accuracy 0.81 something, that is 81% of accuracy. Okay, if you need to find the confusion matrix, same one. This code, give it here. You can put it here on confusion matrix y test comma. This time instead of SVM plot, you need to give SVM RBF plot, because the RBF model output here, the predicted answers is stored in this SVM RBF plot, this variable. So for the confusion matrix, you can write and print it and evaluate. Now coming to checking the polynomial. What polynomial kernel? What we want to do? Just replace kernel equal to polynomial. Okay, very simple. And coming to the train data, put it to the X test data and find the accuracy score. And for here on, find also what? Our confusion matrix. When you try it out, you find confusion matrix. Okay. Now coming to sigmoid. Just give kernel equal to sigmoid, then fit X train and Y train training, then predicting, and then evaluating using accuracy score. Here it is giving around 0.75, that is 75%, and in for polynomial we get around 0.78, that is 78% of accuracy. But for this, what we have done is that we have tried RBF, polynomial, sigmoid, and linear. We tried drawing a straight line. We tried drawing a curvy surface or a complex closed circle. We tried drawing a U-like shape in a polynomial. We tried drawing S-like shape in sigmoid and compare the accuracy. Okay, so here we can see that for this level, our linear and RBF is working better as compared to polynomial and sigmoid. Okay, so the roughly they are giving around 81% of accuracy. Why? Because we can say that linear works well in data in the linear separable form, and RBF works well in the data in the non-linear separable form, the complex curve-like structure. So we can assume that our data set seems to be fall somewhere between linear and non-linear. It is not completely non-linear, not completely linear. So the both RBF and whatever linear is working same. Okay, now when we go to the advanced levels of this type of SVMs, remember that SVM also have many other parameters. It is not for a beginner level, it is just advanced levels like regularization parameter, gamma, degree, like that. So many parameters are there in SVM. By tuning that parameters, we can adjust this accuracy again. Okay, we can tune or we can increase or decrease, or we can compare the accuracies by using such parameters. Okay, to tune that parameter, you need to go deep dive into ML, like hyperparameter tuning, grid set CV, cross validation, and so many internal concepts are there. So if you are interested to research on, you can go and find hyperparameter tuning in SVM, how it's done. You can search it and find it's here on. And in order to understand that, the basics is very important. So we have completing the basics for this webinar. Okay, so we have completed the SVM hands-on. So our decision now is that with this all algorithms, our RBF and linear is better as compared to polynomial and sigmoid for our data set. It may be different for different data set. If according to the data set nature, the working will be different. So we need to try it and find out. We need to research it and find out. Now from the next session, what we use is that do is that we need to check KNN for this data. We need to check decision tree for this data, and we need to compare which is better, SVM or KNN or what decision tree. Okay, for now we are stopping here. We have tried all the SVM algorithms and found that RBF and linear is working well for our data in this scenario. Okay, so with this we are coming to the end of today's session. As usual, we are before winding up. Have a quick MCQ. Okay, the first question: who decides the boundary? So in SVM, I will copy paste in your chat box, then you can read it and answer. Just put the option in the chat box. The question is: in SVM, which data points decide where the hyperplane will be placed? All the points in the data set. Option A. Option B, only correctly classified points. Option C, only misclassified points. And option D, only the points closest to the boundary. Which points decide the position of the hyperplane? Correct. Option D. And these points are called what? What these points are called? We call those closest points to the boundary as dash. Vinaya Century, correct. Separate vectors. Good. Now, next question. Now, it's a big question. You plot a data set where two classes can be perfectly separated by a straight line. You train a linear SVM and it chooses one of the many possible lines. Why does SVM choose this particular line? It's a direct question asked indirectly. So you just read it and first understand it and just answer the options. So you plot a data set where two classes can be perfectly separated by a straight line. You train a linear SVM and it chooses one of many possible lines. Then line. Now what is the peculiarity of that chosen one line? Option A, it chooses the line with the minimum accuracy. Option B chooses the line with closest to all the points. Option C chooses the line with the maximum margin. Option D, it randomly picks a separating line. How that separating line is chosen? Yes, good. Option C is correct. The line that maximizes the margin is the hyperplane or the best fit line. Okay. Now the next question, it's very simple. You use a height and weight of animals and the data clearly forms two groups separable by a straight line. Then which will be the SVM? Very simple question. I think all of you can answer that. You use only height and weight of animals. Yeah. Then the separation is a straight line. Then what is that SVM? RBF, polynomial or linear? Yes, correct. Linear SVM. always remember that straight line, linearly separable data, linear SVM. Not a straight line across the surface, then non-linearly separable data, then it can be non-linear SVM, either it will be RBF, polynomial, sigmoid. Okay, now, so students are classified using marks and the entrance curve. If few students lie very close to the separating boundary, what we will call these students? Boundary points, support vectors, outliers, or soft points. Okay, very simple question, but asked in a scenario. Okay, fine. Support vectors. Yes, B, support vectors. Correct. Okay, good. Now I think it's over. Yes. So today we have come to the end of the 3 session that is about support vector machine. So today we discussed classification, then we discussed what is hyperplane, then support vectors, then margins. Then also we have handled linear and non-linear SVMs. Also we discussed the non-linear SVM trick, the kernel trick. Okay, so we also found we also tried these algorithms in our loan prediction data set, and so today we have got conclusion that either RBF or linear is a better model for our loan prediction data set, but this is not the final decision. We need to try now KNN decision tree and also all the classification algorithm. Then only we will be completing a case study. But for our webinar, we will be trying KNN and decision tree next time. Okay, and then we will compare which is better, either decision tree KNN or SVM is better for. Okay, now our next section will be on December 15th, that is Monday at 7 p.m. So on that day, we will be discussing our next algorithm, that is KNN, K nearest neighbors algorithm. We will check how it works, what is the logic behind that, and how we will implement or how we will do practical using SQL and Python library. Okay, so before we wind up, as we usually do, just fill the feedback door for day 7. Okay, meanwhile, you can, if you have any queries, you can ask in the chat box now. Please fill the feedback form, and meanwhile, if you have any questions, please put it in the chat box. Okay, fine. Remember that this feedback form is also available in your LMS, and also recorded sessions and the material, like the case studies, is also available in the LMS. Also, the quiz is also there in the LMS. You need to attend that quiz to get the CAS certificate. So periodically check the LMS and attend the quiz, and also check if there are any tasks or anything added in that. Okay. So if no more questions, we can conclude for today. And thank you so much for your energy and participation. We come to the end of day 3, and in day 4, we will continue with the next algorithm. Okay, until then, revise the concept, try out the SVM. Remember that you need to rewrite the lab and re-upload the dataset when you try the SVM. Okay, so always remember the lab will be refreshed for every new lab. Okay, keep experimenting, try it yourself, do hands-on practice, then only you will be getting the skill in this machine learning. Okay, so thank you everyone. See you all in the next session on December 15th, Monday, 7 p.m. Thank you once again and happy gun learning. Bye.